Oh, that's right.
Set up.
What are you guys doing?
The interface is like that.
It's raining.
Quite a bit. The implementation quite a bit on.
I answered it. Might as well clean my glasses. They weren't particularly dirty, but the water's already there. And it's mildly acidic, so, you know, for that extra cleaning property. Smog.
All right, so this is our last class to introduce new material. And then next Tuesday is the last class which we'll use to review for the final. So that's what we're gonna do, you know, for this class and also the next class.
Cool.
My scanner broke, so I could not scan the midterms.
Oh.
Well, it can scan, but it can only scan like one page at a time, which is going to take a long time to feed. So I ordered a new roller set, you know, for the scanner from Amazon, and it's same day delivery.
Oh.
So I'm gonna have it like tonight and fix the scanner, so I can do high speed scanning again.
How long does it take you to grade a test?
It depends on what kind of answer I get.
So what's the range?
An average.
Most of the time, it takes about an hour and a half to grade one question.
Okay.
So 4 questions will be in about 4 hours or so. But it all depends a lot on, you know, what kind of answers I get. You know, do I get mostly, you know, if I get mostly partially correct answers where I have to dig to find, okay, you know, where's the problem, you know, how much partial credit should I give, that will take longer. If I get mostly like perfectly correct answer or missing like no answer whatsoever, that will take less time. So it depends a lot on, you know, what kind of answers I get, you know, in the questions. All right, so getting back to graphs, okay, so this is the last class to introduce new material. So there will be new material today regarding graphs. And hopefully we will be able to get to the algorithms, which is the Dijkstras algorithm. Yep.
Are you recording?
Yes, I hope so. Okay, it is recording, but it's good to check. Thank you. It's good to check, making sure, you know, everything is up and running. There we go. All right, so we're back to graph theory, and we're just going to finish up, you know, the terminology of stuff, you know, because, you know, that's what we were talking about on Tuesday. The last topic that we talked about was, you know, what a walk is. So basically, a walk is a string or an array of vertices where each vertex is connected to the next one. But you can have loops. Okay, you can go back and forth between 2 vertices as long as there are edges connecting those vertices. So once we have the definition of a walk, we can now define what a path is. A path is a walk that has no repetition. So now the repetition has to do with the same vertex, the same vertex being visited twice within the walk. Okay, so a path is a walk without repetition. A trail is kind of the same, except this time it is not a vertex that is repeated, it is an edge that is repeated. Is that okay? So this means, you know, a trail and a path are kind of related, but they're not the same thing. Okay, just to give you an example, okay, I keep going back to the whiteboard, but I really should be using the the document camera. And for that, I need to find my pen and turn on the document viewer thing. Well, there we go. Okay, so I'm gonna adjust the distance just so that we can get a bigger display. There we go. Okay. So if I use, you know, the example from before, you know, we have A. This is vertex A. This is vertex B. This is vertex C, and this is vertex D. And I think this is the graph that we had from the class on Tuesday. So if I want to make a walk that has a repetition of the vertex, let's see. Well, I guess it's hard to demonstrate it with this one, so I might need to add some additional edges to illustrate the concept. So I'm going to make one more edge here. There we go. Okay, so if I look at the walk A, B, C, A, that is a walk. It is a tuple. So this is a 4 tuple because it has got 4 items in it, but the ordering is important. This is a walk because A is connected to B using this edge here. B is connected to C using this edge over here. C is connected to A using this edge over here. So it is a walk. It's fine. But it is not a path because there's a repetition. A is repeated. So this is a walk. It is not a path. Yep.
Do we repeat like those connections, or we repeat the letters?
Okay, let's look at the definition again. A path is a walk that has no repetition. And in the example here, because A, B, C, A is repeated. So that's why it cannot be a path.
Cannot repeat the same points.
Cannot have,
Cannot visit the same cities.
cannot repeat a vertex. Yeah, cannot repeat a vertex. And if you look at the definition of a path, let's take a look at this mathematical notation here, just to see whether we understand what it is. Okay, so let's take a look at this description here. X is a natural number, and X is less than the cardinality of P, which is the path. What this is really just doing is to make sure that I is a valid index into the path, because the path is kind of like an array. Okay, so I is a valid index into the path, J is a valid into the path. And what this is saying is, if I does not equal to J, then P bracket I should not equal to P bracket J, which means you cannot have repetitions. That's just one way to define no repetition. Is that okay? Does everybody see how I basically said, okay, no repetition, or the same vertex cannot appear twice in the path? Twice or more, I should say, because if I say cannot appear twice, what about 3 times? Maybe that's okay. Yep, go ahead.
So in your example, if you just had ABC,
ABC is fine. ABC is a path.
it would be a walk and a path.
It will be a walk. Well, every path is a walk. Okay, so that part is okay. But if it's just ABC, then it is also a path because there's no repetition of a vertex. Okay. So the next one is a little bit more tricky because the next one defines what the trail is. A trail is a walk where no edge is repeated. So that means ABCA is also a trail. Because ABCA, even though there is a repetition of one vertex, but no edge is repeated. Because A to B, B to C, C back to A are 3 distinct edges, so no edge is actually repeated. So that one is actually a trail. A tour is a trail where the first and the last vertex is the same, so that means ABCA is also a tour. Is that okay? A planar graph is one that can be drawn in 2D with no crossing lines. And the graph that we just looked at is one of those.
What is crossing lines? What is that?
A crossing line means, okay, if you think about 4 vertices and it's fully connected, then you have to, well, no, 5 needs to have a crossing lines. 4 doesn't need a crossing line just yet. Okay, so let's take a look. We have 4 nodes here, or 4 vertices. And I want this to be a fully connected graph, which means I want connections to each and every single one. And for the purpose of this discussion, it doesn't have to be unidirectional or bidirectional, because if you can draw one edge, you can draw the other way back using the same way without crossing. So we'll just consider this as a non-directed graph. Okay, just a general graph. So these are easy, right? Okay. So now how do we connect from here to here? Well, they can go outside. So this one would still be considered planar because you can draw this on a piece of paper without the edges crossing. But when you have 5 vertices, then you have to cross if it is fully connected. So let's take a look at 5 vertices. Okay. So these are easy. Okay. And this one we can take care of it like this. And we have this one connected to this one. And the one that is crossing is going to be from here to here. There's no way to avoid having to cross something else. Is that okay? From here to here. There's no way to avoid crossing another edge in order to connect this vertex to this vertex over here.
What's the value of knowing that it's planar? What's the value of that? I mean, besides knowing it's a little bit more complex, I mean, what does that either prevent
Well,
you from doing?
personally, I think, well, just from personal application, this is important when you are laying out circuit boards. So when you're designing circuit boards and you're routing the traces on the circuit board, having a planar graph means you don't need another layer of the circuit board. Now I'm pretty sure mathematically there are people who generalize this so that you can have like a single plane planar, double layer planar, and so on and so forth, which corresponds to, okay, what if my circuit board is double-sided? What if it has 3 routing layers, 4 routing layers, and so on? Yep, go ahead.
Can a walk be a trail but not a path?
Can a walk be a trail but not a path?
Or are all trails paths?
A path is one that does not have a vertex repeating.
Oh, okay.
And what was the original question again?
Okay, and now that answered my question.
Okay. I'm just increasing the exposure so that the white paper matches the actual white background. Otherwise, it bothers me. All right, so we got all the definitions done. This is just a description of graphs versus encryption. It's really hard to ask questions about this, so I'm going to skip this, which means I'm not going to ask any questions relating graphs to encryption. But there is a very close relationship between these two. Graph theory is a high-level math class, but it's not taught by math professors. It's typically taught by either electrical engineering department faculty or computer science faculty. And it is usually offered as a graduate level class. And in that class, they will start to get into graph theory, which has a whole bunch of theorems and whatnot, and they will only start to talk about how graphs relate to encryption. So for those of you who really want to get into computer security, and particularly the mathematical side of security, you probably want to get a little bit more involved with math, because graph theory, which is a branch of mathematics, is actually important when it comes to encryption. Okay, but in this class, I'm just going to touch on it a little bit in the notes. I'm not going to ask any questions. So we're going to move on from here to hash functions. We're not going to ask any questions about that. So by skipping both of these topics, I can move on to something that is actually kind of important, because see, there's a reason why I'm skipping all of this stuff here. Because I want to get to the graph traversal and searching algorithms, which I think is actually kind of important. Now, these things, I won't have enough time today, to talk about both Dijkstras algorithm and A-star algorithm, which is down a little bit from here, okay? Because Dijkstras algorithm is here and A-star is over here. A-star is what we call a heuristic algorithm, which means it makes use of a heuristic, a rule of thumb, in the attempt to make the search more efficient. Okay? But Dijkstra's algorithm was the original algorithm to search in the graph to look for the shortest path. Okay? So what we'll do is we'll take a look at Dijkstra's algorithm only, and not at the A-star algorithm, unless we have time at the end of today's class. There are also other types of algorithms. One is called the IDA algorithm. It is recursive successive approximating heuristic state space search. So if you want to classify that algorithm, say that again. It's a recursive successive approximating heuristic state space search algorithm. Yep.
Can you define heuristic?
A heuristic is a rule of thumb that will give you an estimate. So without knowing exactly how much it will cost from one vertex to another vertex, it gives you an approximation. The best way to illustrate, a heuristic function is to look at a map. Okay, so I'll just kind of talk about that because that's a really good question. What is a heuristic? So if you go to maps and we just magnify to this portion here, okay? So if my interest is to estimate how much time it will take from this intersection, of Judy Court and Date Court to this intersection here, of Overbrook and Creek View Way, okay? I can basically just look at the actual distance between these 2 points. And then I can say, okay, on the average, a vehicle can only go, okay, based on the time of the day, okay, maybe 20 miles per hour, combining your stoplights and stop signs and whatnot. So I can give you a very gross underestimate by looking at the straight line distance between these 2 points and just divide that distance by 20 miles per hour. Now, is that estimate accurate? Probably not, but it is still better than not having that estimate. Okay? So that's what a heuristic is. It's a very easy to compute function. It is an underestimate of the actual cost, but it will, in the end, hopefully help to make the search algorithm more effective. So you can get to the solution quicker.
Is it kind of like a starting point? Like you find where you're starting to, like what distance you have to traverse first?
It's not quite a starting point. We use it to prioritize, which alternative to consider first when you're doing a space search. Okay. Yep.
Is it always like a lower bound? Like is it always underneath the actual cost?
Yes. When the heuristic is guaranteed to be a lower bound, which means it's always an underestimate, that property is also called admissible. Now, don't ask me why they use the word admissible to mean it is a lower bound, but an admissible heuristic guarantees that you won't miss the shortest path. On the other hand, if your heuristic can overestimate, then it is possible for you to miss the shortest path. And it kind of makes sense because if you can overestimate the actual distance between 2 vertices, you can avoid a certain path that is actually less expensive than you thought it is. And as a result, if that turns out to be a part of the optimal path, you're going to miss it because you would think another path is actually shorter because of the gross overestimate. So it sort of makes sense intuitively. but that's what admissible means is always an underestimate. Now obviously the function that maps everything to 0 is a underestimate. Now it's not useful, but it's a very special case of a heuristic function that is admissible or always an underestimate. Okay, so are there any questions about the general idea of state space search? Now if you're looking at this from the perspective of Google Maps or FedEx or UPS, it's a realistic problem, okay? Because you do have all of these vertices representing drop-off points, okay? And you want to figure out, okay, what is the most efficient way to drive your UPS truck to deliver all the goods? Now, when we talk about cost, it may not be just time, it can be fuel, can also be insurance, because certain routes may have a higher chance of getting into accidents, okay? So you have to kind of combine all of that stuff into the quote-unquote cost between vertices, or the cost of the edges. So are we okay so far in terms of the general idea of what is state space search and why it is actually useful? Okay. What about optimization problems like register allocation and stuff like that? When we talk about register allocation, it is a job that the compiler has to do. Now, not so much with the i7, i5, or the Intel processor because they are CISC processors, which means they only have a very small number of registers. So for the most part, you cannot really keep a lot of partially computed results in the registers, and you have to use memory a lot, to store partially computed results. But in RISC architectures, it is not uncommon that you end up with 32 or even more registers. So now you can say, hey, the registers can store a lot of partially computed results, and I can just reuse a register later on if a particular result is not going to change, so I don't have to store it back into memory and reread it from memory. That can optimize, or you can make your program go a lot faster. So the optimization of what you want to store given a limited number of registers turns out to be transformable into a state space search algorithm, a state space search problem like the traveling salesman problem. So even though it looks like we're only solving problems in terms of maps and navigation, that is not the case. State space search is a very general problem that is applicable to a lot of different types of problems. Okay, are there any questions before we move on to the actual algorithm itself? No questions? Okay. All right, so what we'll do is we are going to follow a hyperlink. Yep, I was tempted to order these, and then I found out that on eBay, you can get these for 1/3 of how much Amazon is charging. And I'm looking into these because I don't want to have to borrow your batteries. And I do have my own batteries now. I remember to bring mine, but sometimes I forget. And if the alkaline runs out, then I have to run to the lab. And if they close or they don't have alkalines, these are nice because you can plug it into a USB port to charge them. So you don't need your own charger. You just need to plug it into a USB port. And I don't think they're particularly fast, charging, but it's the convenience. Okay, I can have 2 of these things, plug into the computer, and they will stay charged. I like window shopping, especially if somebody else is paying for it. All right, so we are looking for my current topic and looking for the Moodle part. And Moodle is going away, not that it will impact any one of you here. It's going to go away in about a year, and so will D2L. So D2L and Moodle will both be replaced by Canvas.
How long have they been using
Canvas,
D2L?
C-A-N-V-A-S. Huh?
How long have they been using D2L?
I'm guessing maybe 6 years or so.
It looks like it was designed in like 2001.
Well, Moodle is even older.
And Moodle's better than D2L.
You think so?
Yeah,
Well,
D2L is garbage.
the one part that I don't like about D2L is it tries to open frame, inside frame, inside frame.
Yeah.
So you have like 3 sets of scroll bars to scroll around, but you have a smaller screen. Like if I were to use D2L to teach my classes, you will see like nested scroll bars. Yep.
Wasn't there one before D2L?
Yes, that was Blackboard. And Blackboard was unstable, so to the point where people taking online classes and they're taking exams, it would drop people out of exams. So you can be, so it's not like it doesn't even let you into the exam. It will let you into the exam, and then it will crash to the point where it will drop you out of the exam, and then you cannot get back in. Okay. See, Moodle, I can crash this computer in the middle of a test. I just have to sign in to another computer to my Moodle account, and I can continue the attempt. So Moodle is okay. Maybe it's a little bit slow sometimes, but it is actually functional. And Blackboard was not functional at the time. All right, so what we'll do today is to take a look at Dijkstras algorithm. Because of all of these algorithms, Dijkstras algorithm is actually the simplest one. All right, so this is Dijkstras algorithm, and we'll skip straight to the algorithm itself in pseudocode. Okay, and this is the pseudocode of Dijkstras algorithm, which it looks kind of complicated. Okay. So instead of just reading the algorithm, what we'll do is we'll go through a few examples. Because once we go through a few examples, it's not going to be as intimidating. So to go through the examples, I'm going to use my trusty document viewer so that I can draw pictures, and everything is going to be screen recorded. And we can use. Now, it won't be very interesting unless we have alternatives, okay? So we definitely want to draw graphs that has alternative paths, okay? So the one that we had before is not a bad one, but I'm gonna make it a little bit simple this time. Okay, so now we have a few alternatives. This is vertex A, this is vertex D, this is B, and this is C. So the labeling of the vertices is still the same as before. And now we have to associate a cost to each edge, because then we cannot because otherwise we cannot say how much is this path. Okay, so you have to associate cost to each path. We'll make it kind of extreme. Okay, so we'll say this is 2. No, or maybe not. We can make this 2. This is 4. This is 1. This is 1. And we'll make the other one kind of expensive. So we'll make this a 6 over here. There you go.
Hey, Jack, how did you make that shadow go away?
The shadow is still there. It's just that I increased the exposure to the point where the shadow is kind of washed out.
Yeah, I noticed that.
It's a side effect. I can still see it myself.
I know.
It's just that you cannot see it on the screen.
I'm looking at that. There's no shadow. That's cool.
How do you make a shadow go away? You invite a Vorlon. And some people go like, what? What is a Vorlon? You have to watch Babylon 5. All right, so this is our graph, and our idea is to go from A to D. Okay, so we want to go from A to D, but we want to find the shortest path. We don't want to just find a path. We want to find the path that has the least cost. Okay, which means when you add up the cost of each edge of that particular path, it will have the least amount. Is that okay? All right. So we start with A. Okay. So we always start with a set that is your starting point. Okay, so in this case, my starting point is A, and so that becomes my set. And the next thing you want to do is to consider all the neighbors of A. Now, when I say a neighbor, it means the vertices that are directly connected to A by an edge, where you can go from A to those edges. So in this case, the neighbors of A would be B and C. Okay. So now you say, okay, from A, I'm going to take A out, okay, and A is already considered. I want to look at B, I want to look at C. Now, when you look at B and C, you also want to calculate from the starting point, which is A, how much is it going to cost me to go to B? Well, that's pretty easy. To get to B, the cost is going to be exactly 2. To get to C, the cost is exactly 6. Now, whatever the unit is it doesn't matter. Okay, it can be minutes, can be dollars, can be gallons of gas. Okay, it doesn't really matter. So now, out of B and C, I'm going to have to choose one, because A is already expanded, what I call expanded, which means it is already explored. If one vertex is already explored, I don't have to explore that again. B is not explored. B is just touched at this point. C is not explored. But out of these two, I have to pick one to explore. Which one do you think I should pick to explore? I should pick B to explore, and why not C? Because it's already expensive. It's already too expensive to go to C, which also means if I explore C, any other, if I go from C to any other vertices, it's going to be more expensive to go to B, which means it's not likely that I can find the shortest path going this way. Okay. Okay. So we're going to leave B alone. We're going to leave C alone, and then we'll explore B. Okay. So now we have to track. Okay, from B, where can we go? Well, B can go to 2 places. B can go to C, and B can go to D as well. Okay. Now it gets a little bit tricky, because even though we have been to C before, where the cost was 6, Now we have a new way to go to C where the cost is actually less than what it was. Okay, so now we have to update and say, oh, we found a new way to go to C going through B, where the cost to C is only 3. And then the cost to go to D, which is our destination, is a 4. Oops, I take it back, it's a 6. Because it takes a cost of 2 to go to B, and then from B to D is a 4. So the total cost to go to D is a 6. Now you might think, oh, we have just found the shortest path because we are now at the destination. Well, that is not exactly the case, is it? Exactly. So now we have to explore, out of the options, we can expand D, but if D is already the destination, so we have no choice but to expand C. From C's perspective, it only has one neighbor. C has one neighbor, and that turns out to be D. From C to D, it only costs 1, but to get to C itself, we only need a cost of 3. So to get to D, we now have a lower cost of getting D of only a cost of 4. So this is actually a pretty good example of, we are trying our best to find the shortest path, but as we go through what we think is going to be the shortest path, sometimes we would actually end up finding something that is even less expensive. Is that okay or not? Yep.
What if you end up taking, you think the shortest path, but you end up having more cost than you would have went to C?
Say that one more time.
So what if you were to go to A and then you'd see B and then you'd see C and then maybe had another point and another point after that, and it would end up to be bigger than it was originally to go from A to C?
Then you step back, right?
Okay, so the cost from A to C is known to be 6. So you're saying that there's an alternative path where the total cost is greater than, then you will use the original one. In other words, there's a way, the algorithm has a way to track. In order to come to this node, in this case is C, in order to come to this vertex C, which way to come here is the least expensive one. There's a way to track back. Okay, who is my previous node? Yep, there was another hand.
So this is basically a methodical way to try every path.
It's not trying every path. In a more general graph, it is actually only trying the ones that are likely to contain the shortest path.
Okay.
So the ones that are not likely to contain the shortest path is not going to be explored.
But that would be more obvious with a complex graph.
Right, because this one is too small to illustrate it. So if you look at, in general, I'm going to use a different piece of paper because I want to get back to that one. Okay, so in general, if you have a complex graph, so let's say you have a complex graph, that the boundary is this much, and you're trying to go from this vertex to this vertex over here. Okay, so the exploration of the algorithm will only explore what is likely to be on the shortest path, and stuff that is outside of that range will not even be explored. So it doesn't guarantee to touch every vertex. It only guarantees to touch the vertices that are quote unquote likely to be the shortest path, and it guarantees to find the shortest path. But if there are alternative shortest paths, it is only guaranteed to find one of them. It doesn't guarantee to find all the shortest paths. Yep.
So does this algorithm find the shortest path to every node?
No, it only finds the shortest path to a particular node, to a particular vertex. And by the way, a node is also a vertex. So sometimes I use one word and sometimes I use the other word. Yep.
If as you're going through the algorithm, you find a faster way to get to, say, C. And so, like in your case, so you find a faster way to get to C. Would you stop the next time you run through the algorithm, not have to make that move because you would know that that path to get to C would be
Let's
faster?
go back to that example. So what is going on is when I expand node vertex A, I immediately know it will cost me 2 to go to B, and it will cost me 6 to go to C.
Yeah.
So at that moment, the shortest path or the shortest distance to C from A's perspective is actually 6.
Yeah.
However, when I expand from B and explore from B's perspective, then I know there's a shorter way or a less expensive way to get to C. And at that point, the algorithm has a way to keep track and say, oh, I don't want to come from A from C's perspective, I want to come from B. In other words, there's a quote-unquote back pointer to point back to the vertex that is on the quote-unquote shortest path to that particular vertex. Okay? Now, I'm not showing you the algorithm yet, so it might sound confusing, like, okay, how do we keep track of all this stuff? But I want to show you this example by hand first, so that when we do go over the algorithm, you're already familiar with the map, and then we can just take a look at the algorithm itself and figure out, okay, how does it keep track of all this information and use the algorithm to find the shortest path. So are we still doing okay so far with all of this stuff here? Okay, all right. Okay, so now we're going to go to the algorithm, which is kind of nasty looking. And I want to make sure that we can show the lines correctly and not having the comments to wrap around it. That's the issue because it has a lot of comments on one side. So this is the whole algorithm, and it's definitely, you can see that it has two concepts. There are two concepts involved here that is kind of related to what we have talked about. The first one is the set concept, okay, because the vertex set Q is a set, okay? And it also has the concept of a function, but you don't have to look at this from the perspective of a function. You can look at this as an array. But in this, it's an array where the index is the vertex, so that, dist in square bracket V is giving you the distance from the start vertex to vertex V. So in a way it's a function, but the implementation is more like an array. It's more like a map, for those of you who know what a map is in C++, in a template class, that's more like a map. If you know PHP or Perl, it's more like, how do they call those things? Sorry?
Dictionary in Python.
A dictionary in Python or hash in Perl, but they're basically the same thing. It uses the indexing operator, but the indexing can be done with a string or anything that can be compared. Okay, so those are the main concepts here, and you can also see while Q is not empty, that's definitely a concept in set theory. The syntax of this is for the most part Python. Okay, we don't see a begin, end, or open and close curly brace. So it's basically just Python syntax, but integrating into it would be the concept of using set. So there we go. So we'll go ahead and use this algorithm, and I want to find a better way to superimpose stuff. So let me see what would be the best way to do this. Move this to a new window first, so I can move this around like so. Oops. Then I can put the map itself on top of the algorithm. Here's the algorithm, here's the map, and here we have those two superimposed. Okay, so we're okay. And now we just need to add one more piece of paper so that we can keep track of the changes to all of these variables. Okay. So I'm going to move this one up as much as I can, push it to a corner like that. And have another piece of paper down here to really just do the trace. There we go. All right, so we will go ahead and follow the algorithm. On line 3, we just create a new set Q. And when you create a new set, it is going to be an empty set. Is that okay? And then we move on to line 5. Line 5 to line 7 is a loop. I'm not going to go through all the iterations. because all it's really doing is to initialize the two arrays or the two hashes or the two dictionaries or the two functions, okay? You can look at it in any way you want. But it's basically just saying, okay, initially the distance to all vertices is infinite. And at the same time, the previous node of, or the previous vertex of all the vertices is unknown. Because there's no solution yet at this point. Okay, this is the starting point. Yep.
So previous is based off of the shortest cost path to that vertex?
Yes, previous is basically saying, okay, who is the previous vertex that leads me back to the origin, the source on the shortest path known at this point. Okay? Does anyone want me to say that again? Previous, PREV, is basically, you can look at it as a function, you can look at it as an array, but it basically pre-V is the vertex that is on the path back to the source, and it is the shortest path known at this point from the vertex of V. Yep.
So like if we could give an example, so if we had like a map with, or I mean a graph rather, with like A, B, C.
Mm-hmm.
So for the value C, there would be like B if B was the previous one on the shortest path to C.
Right, but only if B is known to be on that shortest path at that time.
Okay.
So initially, since we have not done anything, we don't know, who is going to be there. So initially, they're all unknown.
And how do we know the like the from and the to?
Sorry?
Like the initial point and the intended destination. How do we know those?
It is passed as a parameter. So in this case, it is passed as source. So source is a single vertex that is the origin of the entire thing. Okay. So what I'll do, this is the first time I do it this way, so bear with me a little bit. So what I'll do is I'm going to also draw a picture here with all the vertices, A, B, C, D. So initially, what the algorithm is really saying is the cost to each of these vertices is infinite, which means nothing is connected. Okay, we don't know any path. And also, because nothing is connected, there's no such concept as, oh, who is right before this one? So that's why the previous is also undefined. So that's the initial state. So I'm not going to trace through lines 5 to 7. And line 8 is adding V to Q. That doesn't make any sense in the loop to do this. It is part of a loop. Line 8 is part of the for loop. Well, okay, so we'll go ahead and just do that part too. So Q will become A, B, C, D, just like that. And then we get to line 10. Now line 10 is the actual beginning of the algorithm, because it is actually making use of the source, which is a parameter to Dijkstras algorithm. You can see source is over here. It is basically, okay, where do we start? In this case, we're starting with vertex A. So that means the first thing we do is the distance to vertex A is 0. Okay. So on A here, we'll just say dist is 0 to indicate the distance to vertex A is 0. Well, that makes perfect sense, because if I want to get to vertex A and I'm starting at vertex A, how much distance do I have to travel? Nothing, because I'm already there. Okay. All right. So that's the beginning. That's now we're done with all the initialization. On line 12, it's a loop. Okay. So line 12 all the way down to line 21 is a loop, and then we have a loop inside of a loop. This loop is not going to stop until Q is empty. In other words, in this particular case, this algorithm finds the shortest path from the source to every single vertex. Not just one single vertex that we're interested in, but to every single vertex. Now, that really kind of sets Dijkstras algorithm apart from some of the other search algorithms, which are only interested in going from one vertex to another vertex. This one is saying, okay, from one vertex to all of the vertices, let's find out what is the shortest path to all of them. So on line 12, the first time, Q is obviously not empty because it has got A, B, C, D in it. So what we want to do is to go to line 13. Line 13 is choosing one of the vertices in Q with the smallest distance. So when you look at the distances, B has a distance of infinite, C has a distance of infinite, D has a distance of infinite, A has a distance of 0. Well, which one has the shortest distance? Of course, it's going to be A. So on line 13, we choose vertex A to become U. U is a variable, A is a vertex. Are we okay on? Oh, I'm not showing the line numbers. There we go. That's better. Okay, that's on line 13. And then on line 14, we want to remove this element from the set. So that means Q is now just B, C, D, because A is now removed. Then we get on to line 16 to line 20. So when you look at line 16 to line 20, it's basically expanding. It's expanding from U, in this case, U is the variable. But since U is vertex A, I'm looking at things from the perspective of vertex A and say, okay, who are my neighbors from A's perspective? A is going to say, B is my neighbor, C is my neighbor. So what am I doing for each neighbor? For each neighbor, I have to first go to line 17 to compute the alternate path. Basically, I'm just adding, since I know the current known shortest distance to myself is this bracket U, which is 0 in this case, I just need to add the edge, the cost of the edge to my neighbor V to come up with the potential distance to that neighbor. And then for that distance, okay, I go through this logic here, and I say, is the known distance to that particular vertex greater than the new distance? If so, we want to update it. If not, just leave it alone. Yep.
Are neighbors only based off of their position in the set? So the neighbors of B is C.
A neighbor vertex is a vertex that is, okay, a neighbor V of U in this case means an edge goes from U to V. So a neighbor is a vertex that is directly connected by an edge. Okay, yep.
So even though you don't have it in your diagram, I'm sorry, I was thinking about the other diagram.
Okay. Well, let's go ahead and apply the loop from line 16 to line 20 to the graph that we have at this point. Okay. So the first neighbor, you can choose C to begin with, you can choose B to begin with, it doesn't matter which one you choose, okay? So we'll just go ahead and choose B first. So we'll choose B to be my neighbor V of U, and variable U is actually vertex A at this point. So the first thing we do is to say, okay, it costs 0 to go to A, and it costs me 2 to go to B. The known distance to B at this point is based on the initialization, which is infinity. It's because of the initialization up here. So the known distance, to begin with is infinity. So the question now is 2 less than infinity? Well, I think so. Okay. So that means we have to go to line 19 and line 20 and update that information about V. So now we start to say the current known shortest distance to B is 2, and the previous node that will give me this cost of 2 is A. And then I go through the second iteration of the for loop, and this time I process neighbor C of A, and I go through the same calculation. C originally has a distance of infinity. The new cost is going to be the distance to U, and remember U is vertex A, plus the edge cost going from A to C in this case. The edge cost from A to C is 6. So alt is 6. The question now is 6 less than infinity? well, 6 is less than infinity, so it's time to do some updates. So now I say the distance to C is now 6, and the previous node getting to C with this cost of 6 is A as well. Are we doing okay so far with the updates? Yep.
I'm wondering, why isn't D considered a neighbor? Or how would it know which is a neighbor and which is not?
D is not a neighbor because there's no edge connecting from vertex A to D. Yep. Mm-hmm.
So is the comparison line on line 18, like if all is less than distance B, is that saying is the current path less cost than the known paths to that node already?
Yep. Because it's possible that we already have a distance to that particular vertex, but you can discover a shorter distance later on, and this allows us to update it. So we're not only updating that this is now the shortest, the shorter path or the shorter cost to get to this vertex, but it also uses line 20 to remember, oh, how did we get here to make use of this shorter cost? Oh, you have to get here from A in order to get the shortest path. Okay? So are we still doing okay so far with this code? Okay? So now we're done with the loop, and with the end of this loop here, we go back to the while loop, and we look at the set Q, and we say, okay, is it empty? Not quite, because the set U still, the set Q still has 3 elements. It has B, C, and D in this case. So now we just have to say, okay, let's pick one of those and expand it. But the picking criteria is we have to pick one that has a minimum distance. And then you say, oh, we already know who has the minimum distance, A. We cannot pick A because A is not in the set Q. So out of the elements in Q, we have B, C, and D. B has a distance of 2, C has a distance of 6, D is still uninitialized. Okay, let me move that around here. D is just initialized to infinity. So that means out of these 3, I'm going to choose B to expand. So that means the next time I get to line 13, U is going to be vertex B, and then on line 14, I will get it out of the set Q. So now Q only has C and D remaining. And then we go to the loop on line 16 to line 20.
Can't see.
Oh. Okay, we have a. I need something that can scroll, or I can do this.
Lift up the camera.
Hmm?
What if you lift up the camera? Give it a wider.
I know how I can do this. I can fold. Or I can lift the camera, zoom out. This class is getting high-tech and low-tech at the same time. Okay, so now we are going through line 16 and line 20 again. But line 16 and line 20 is basically just looking at B and saying, okay, who are the neighbors of B? Let's see if we can do some updates with those particular neighbors. Okay, so that means in this case, okay, I'm just going to go through the new map here. So there we go. Okay, so we look at the new map, and we are now looking from B's perspective and say, who are my neighbors? Well, B has a neighbor D. It also has a neighbor C. Let's deal with D first, okay? Because there's no prioritization of which neighbor to consider first. It doesn't really matter. So we'll consider D first. And the first thing we do, according to line 17, is based on the known shortest distance to B, let's compute how much it will cost to go to D. Well, since it's costing me 2 to go to B, and the edge going from B to D is 4, that means the cost to go to D is going to be 6. Okay, so we say the current known shortest distance to D is going to be 6, and in order to give me that cost of 6, the previous vertex is going to be B. Okay, so those 2 updates are due to line 19 and line 20. Now we apply the same thing to guess what? C. So we look at C and say, okay, C, you are also a neighbor of B, so we're going to go through this computation. But since it only costs us 2 to get to B at this point, and the edge to go from B to C only has a cost of 1. So that means the new distance to go to C is only 3. In other words, the condition of line 18 is now true, because I have just found a shorter way or a shorter path to go to C through B. And as a result, I'm going to go to line 19 and line 20. I'm going to update the distance to 3, and I'm also going to update the previous vertex to B exactly. Is that okay? So now I'm done with the for loop because I have considered all the neighbors of B. And now I go back to line 12, which is the while loop. I look at the set Q. Okay, at this point, the set Q has 2 elements left, which is C and D. I have to pick one that has the shortest distance. Okay, so out of those 2, C and D, C has a distance of 3, and D has a distance of 6. So out of these 2, I'm going to pick C. As a result of doing that, I'm going to say U equals to C, and then Q, oops, cannot see that. Q is now just a single element of D. Okay, so we're going to do the same thing. Now we look at things from the perspective of C, and we say, okay, who are the neighbors of C? Well, C only has one single neighbor, which is D, and we'll apply the logic from line 17 to 20 to vertex D in this case, because that's my only neighbor. So the question now is, if I just add 3, which is the current known shortest path to C, to the edge leading from C to D, then I have a total distance of 4 going to D. Well, is 4 less than the current known distance to D?
Yes.
Yes, it is. So we have to update the distance. Okay, you cannot see that. Okay, so we have to update the distance to 4. And we also have to update the previous, because in order to use this shorter path, I have to be coming from C. So previous is now updated to C. And now I'm done with the for loop because there's only one neighbor. I go back to the line 12, which is the overall loop. I still have one element left in Q because Q has one single element of D. So for this last iteration of the outer loop, U is going to be just D, and then Q becomes an empty set. And you can definitely tell that this algorithm will terminate, because for each iteration of the outer loop, we guarantee to remove one element from the set Q. So if the set Q has a finite number of elements to begin with, in a finite number of iterations, we will terminate. Yep?
What do we do if we have like a directed graph where a vertex is unreachable?
Then that vertex will, well, that's a good,
Because it will never
no, it will still be removed. No, it will still be removed because when you look at line 13, when you are only left with vertices that are unreachable, you will still be forced to take one of those one at a time.
Okay.
Because even though infinity is infinity, you're still performing line 13. So it's just that they will be the last ones to remove from the set, but the algorithm will terminate. So we are getting to the last iteration with D. Now D is easy because in this particular graph, D has no neighbors. D has only incoming edges, it has no outgoing edges, which means the for loop of line 16 to line 20 has nothing to do. So we get back to the while loop, but since Q is already an empty set at this point, we get out of the while loop, and then we get to line 22, which is the return statement. So now we can just return, all the previous and all the distances. So this time we have the shortest path to every single vertex in the graph, not just one single one. If you ask me, oh, how do I get to this vertex? I have the shortest path. How do I get to that vertex? I have the shortest path. Because prev, P-R-E-V, is keeping track of okay, in order to get to me in the shortest path, who do I have to go through? And by tracking it backwards, you can find the shortest path. Okay, Mickey first, and then, yep.
Okay, so on line 22, you said return all the distance and all the previous?
Yep, because that's what it's saying, is returning the entire map, hash, or dictionary.
Okay.
Okay, go ahead.
If D had neighbors, would you consider them even though our goal was to get to D?
Well, the algorithm doesn't use the parameters do not identify what is the only destination that you're interested in. So it will not terminate until it solves the entire thing. But it cannot stop early because, as we saw a little bit earlier, if you stop early, like as soon as you know a certain distance to a particular vertex, that doesn't guarantee that it is actually the shortest one. So without exploring all the vertices, in this case, you cannot guarantee to find the shortest path. Yep.
So it actually does find the shortest distance to every vertex?
Yes. Yep, it finds the shortest distance to every single vertex, along with how to get there. Yep. Okay, any other questions? No other questions? So this is all good? Sorry? Let's do A star. Well, A star, okay, I will show you what A star looks like first. Maybe you guys will change your mind. A star is a little bit more involved because it makes use of heuristics. And you can see in Dijkstras algorithm, we don't use heuristics at all. We just keep expanding based on the known distance to a particular vertex, but not an estimate distance between a vertex and another vertex. A star does, okay? So we'll take a look at A star, and you guys can see whether you want to go through that or not. So here's the pseudocode.
No.
Okay, we don't have to do the reconstruct path, but the actual algorithm is a little bit more involved. There's a lot of commenting in between as well, but A star is actually more complicated. But it does help because you are making use of a heuristic function. So I think I'm not going to go through A star, just because we are running out of time. But A star is interesting because of the fact that it makes use of a heuristic. But I do want to give you another example, okay? I'm going to use a piece of paper to illustrate that. Okay.
Professor Zach, if you have multiple costs associated with like the traversing from one node to another, so like you have costs of say fuel, time, and maybe like wear and tear on your vehicle or something.
Okay.
Do you combine those into like one overall?
Yeah, you have to combine all of those into a single number. Yeah, you have to combine all of those into a single number. So if you're running a company, you usually just boil everything down to just dollar amount. I'm just gonna zoom out here because it's gonna be. It might take up a little more space. And this one relates to micro mouse competitions. Okay. So before we do that, we have enough time to complete this demonstration. So micro mouse is a competition, a robotic competition, and UC Davis used to compete, in these events when I'm still teaching that class over there. A few years back, you guys remember there's a financial crisis with the UC system, not just UC Davis, but the entire UC system had a financial crisis. So UC Davis, or at least the electrical engineering department, decided to let go of all the lecturers. Basically, the lecturers are usually part-timers as well. So the part-time lecturers, which are equivalent to our part-time professors over here, except the prestige is even lower because there's a difference between a lecturer versus a professor. Okay, And if you're a part-time lecturer, you're basically at the bottom of the totem pole, which means your pay is also the lowest compared to how much time you spend to teach classes. And they decided in order to save money, let's get rid of those people first. And as a result, I'm not teaching there anymore. But I used to teach the micro mouse class over there, not for the money. The money was not really that good, but it was a lot of fun. So I'll show you what a micro mouse competition looks like. And if we can pull a video, that would be even better. And we can pull one that has Davis in it. 2008? Okay, let me see. I can get the computer to.
Wait, are you in this?
I don't think so.
That'd be interesting.
I'm probably sitting in the background somewhere.
There he is.
I'm probably sitting in the front row because I'm usually supervising the whole thing. Oh, there we go.
Okay, so Tech wants me to talk about the mouse.
Well played. No, that's not me. It just has the same kind of voice.
It reads the walls and updates the walls in its memory. Once it updates the walls, it assigns a number basically to each cell that it's in. And this number gets slightly lower and lower as it gets to the center. So it always wants to pick the lowest number that it can get and get to the center as fast, right? This is the hard part right here. That was hard because the walls are, you can see there are no walls to the sides for the crunch, so it's very hard to error correct for the mouse. So it had to be very accurate in going down here. And then it decided to turn it into the center because it thought that there would be a clear path until it hit that wall right there. Just kind of messed up the tag. Because the mouse thought it was going to get in it, but now it has to go around.
All right. So that's the micro mouse competition, and these mice are really slow. If you want the really fast ones, you want to look up micro mouse, Japan or something like that. They're insanely fast. These expert class, mice.
Did you know T-Mobile's coverage? Think again. In the last year, we've doubled our LTE coverage. Our new extended range LTE now reaches twice as
That's why I don't put the advertisement on mine.
See for yourself at T-Mobile.com/coverage.
This is actually slow. This is still in exploration mode. When you go to a speed run, you will see how fast it can go.
Does it learn it and then just runs the best path?
Yeah. It will try to find the shorter path. Once it finds a path, it will know whether it has found the shortest path. So when it finds the shortest path, then it will do what we call a speed run. And a speed run is insanely fast with these professional expert class mice. Okay, it has found it. Now it's going to do a speed run at some point. This is not a speed run, I can tell. It's still exploring.
To try all the ways that it didn't go before.
Once it knows, it's in a portion of the map that it has already explored, it goes like super fast. Yeah, that's.
Wait a sec.
No, wait.
Yep, it knows there's no shorter path from the end. That's the origin. Okay, now it's going to do a speed run. Yeah. So it can, but this is a real application of the Dijkstras algorithm because with a twist to it. Because initially the mice or the robots do not know about the configuration of the maze. In other words, your graph is not even fully formed yet. Okay, everything is fully connected, or I should say, all the neighboring cells are all connected. So as you start to put as you discover new partitions or walls, you are updating the map on the fly as the mouse is navigating in the maze, and at the same time, it will look at its current position and say, okay, based on what I have learned so far, what is the shortest route to the center of the maze, which is the destination. So it's basically applying Dijkstras algorithm or something similar to Dijkstras algorithm. Is usually a simplification because this type of graph is obviously, okay, out of all the terms that we have talked about, this graph is going to be, starts with a P, it's a planar. It's planar, okay, because the whole thing is on a plane, okay. So it has a specialized version of Dijkstra's algorithm, and we can run it really fast. Like with an 8-bit processor running at 16 megahertz, my algorithm can recompute the values of all the cells, apply Dijkstra's algorithm 40 times per second. And that's using a 16 megahertz 8-bit processor.
So do they just have a node for every square and they're just using the entire grid, or okay?
Yep. Mm-hmm. Yep, go ahead.
So what are they using to detect the wall? Is it a touch sensor?
There are several ways to do it. You can use mechanical touch sensors. You can also use reflective sensors. So the typical way to do it, there are two ways to do it.
Like ultrasound,
You can. Ultrasound is not reliable. You can use ultrasound for a very close object, but when you're looking at like the end of the hallway, it's not accurate. So what they usually do are reflective IR sensors, which shoots out an IR beam or infrared beam, and then based on the amount that is reflected back, or based on triangulation, you can kind of infer the distance between the mouse and the wall that your IR is hitting.
Does the wall have to be made out of something kind of reflective then?
Sorry?
Doesn't the wall have to be made out of something kind of reflective?
Yes, the reflectance of the wall is guaranteed, so it's guaranteed to be like 85% or more, and then the floor of the maze is guaranteed to be painted black, which means the reflectance can be maybe 15% or less, or guaranteed to be 15% or less. So there are certain things that are guaranteed based on the configuration or the physical aspect of the maze. The walls are 18 centimeters center to center in a maze, so you know the dimension of every single cell in the maze already. And this used to be a really fun class to teach, because my students do not just go buy a robot kit, put it together and download the program, put it onto the robot, and call it a day. They actually have to design the mechanical chassis. They have to put everything together. They have to shop for the stepper motors, and some people turn their own wheels. Okay, the actual wheels on the robots. You can either buy or you can turn it on a lathe. And some people actually turn it on the lathe. I mean, it's not really that hard to turn one on the lathe. They design the circuit board. They have to specify which MCU or microcontroller unit to use, and then they have to design the circuit. They have to lay out the circuit. The only part that they do not do is to edge the board itself. So we send out the Gerber file to professional printed circuit shops, and then we get the printed circuit boards back, and then we still do the soldering, and then we have to test the board, and then they have to write the software, debug the software, and so on. So this is really a full product development cycle. Even the teams that did not make it, like their mouse did not solve the maze at the end of the 3 quarters. It's not a 1 quarter class; it's a 3 quarter class. So even the teams that did not make it to the end, like they made something but they didn't work, they still come back to me and say it really helped in a job interview, because they can be honest with the interviewer and say, "Yep, we know how not to do things now." And that still gave them an edge, as opposed to students who did not go through these project classes, who cannot even say what not to do in a project. I'm not sure whether you guys are getting it or not here, but knowing what fails and what does not work is valuable, as opposed to not even knowing what will fail. I have had students, in this particular class, as hiring manager for other students, later students, and they did not even know each other because they have never met. And through the interview process, they will say that one person will go like, oh, I see that you have participated in micromouse at UC Davis. So did you take it from TAC? Yep. Well, guess what? I did that 8 years ago. So I actually ended up with students, older students who took the class as hiring managers of newer students coming from the same class. It was a really fun class to teach. So the algorithm in this case is a little bit simpler, but it is still what we call Dijkstras algorithm, and I have a much better name to name it. Okay, so let's consider a much smaller maze in this case, and we will just give it a certain configuration. That doesn't look very challenging, does it? Okay, all right. So we'll try to go from here to, let's say, over here. So this is my destination. Okay. So in a micromouse application, you're not really particularly interested in where you start. You only want to know where you need to end up with, and how much it will cost from each cell to get to the destination. Because as you're traveling, as you discover new walls and new partitions, you have to update the map. So it's the destination that is the most important. So you mark the destination with a 0 first, and say that if I'm already at the destination, I don't have to travel any further. Okay? But what about the adjacent cells to the destination? It will have a cost of 1. Okay, so these two cells will have a cost of 1. But not this one, because this one is not connected. There's a wall separating the destination from this cell. So then you mark the other ones with 2s, okay? And then these ones with 3s, 4, 5, and then you have 2, 6, because from the 5 you can go from either one. Then you have a 7, 7, a 7, 8, and 8. So the way these numbers are assigned is actually based on the Dijkstras algorithm. But this is a very special case where you don't need to explicitly remember all the edges, because once you know where the partitions are, then you already have implicitly known which cells are neighbors of each other. And also, this is not a directed graph because it is symmetric. It doesn't take turns into consideration. In other words, going from one cell to another cell is always going to be the same cost. Even if there's a turn involved, it will still be the same cost. Let me just show you an example. It cost me 2 units to go from here to here, but it's a straight line. It only also cost me 2 units to go from here to here, which involves a turn, definitely will involve a turn. So it's not optimal. But at the same time, the simplified version of this algorithm allowed us to use a much faster algorithm. And that's why even with a 16 megahertz 8-bit processor, a C program can still recompute all of these values 40 times per second. Now, I had to do a lot of optimization to get it to happen. And so the software people writing the actual programs on these controllers, the initial task is to finish the algorithm, and I explicitly told them, do not use C++, do not use the set template class, do not use the map template class, use bitwise operations. Because these controllers only have 4 kilobytes of RAM. Once you import a class, you're over. It's all over. And this is also where the real-time kernel that I talked about earlier, I guess not in this class, but in my 310 class, these students also sometimes make use of a real-time kernel. So they have the real-time part, the low-level stuff like motion control, that's high priority. You cannot miss too much time. But when it comes to actually computing the algorithm, computing the values, that can wait a little bit. You can sit in the cell a little bit and wait a few milliseconds. It's not a big deal. But it was a fun class, and the reason why I mentioned this has to do with the application of Dijkstras algorithm. So are there any questions about this? So if I ask you guys to implement a micro mouse in the final exam, you guys would not have a problem with that. I mean, it only takes 5 students in each team, 5 units of courses to finish, a project like this. Sometimes, and sometimes, they put in all that time and nothing happened. Well, okay, not quite nothing, but they cannot accomplish the objectives. All right, so this is the end of all the material, and then on Tuesday, we are going to have the final exam review. So you might want to kind of go over everything yourself first and bring all your questions, then we can talk about those questions as well. Yep?
You're not going to go over the mastermind answer example?
Which one?
Your last slide, mastermind answer example.
No. Yep. We only have time up to this point, and that's all. Okay. Turning the mic off. If I don't need to listen to myself, I'm not gonna.
You stopped the recording? Did you stop the recording?
Not.